Okay, so we're trying to do some word problems today. Let me put myself in the speaker view there for the live stream. All right. So we're going to try and understand word problems with physics. And there's some subtleties there. Hold on a second. I got to hit a button here. Okay, got that. And then we'll go back to here. There we go. So let's start with a screen share. Let's go here. Whoops, it's over there. I bring it back over here. All right, and oh, that's chapter 3. We don't need that right now. Let's just go right here. Probably about right here. Oh, no. Sorry, a little more. Sorry, I forgot I wasn't ready for that. Oh my gosh, come on. Let's do this. There we go. That's faster. All right. So just a quick review from last time. Sorry, so much scrolling for online learning. Stinks. Here's your definitions on page 21. So if there's a term you don't know, you could remember that's there. We talked about this last time about these equations having an implied I hat. We're going to work on that today, and I'll hammer some questions as to I'll try and quiz you on that at certain points. And be aware, sometimes we write those equations like this instead. And so you're going to see me sometimes use x final and x initial, or sometimes use delta x. Lately, I seem to like delta x more than the other one, but when I grew up, I always did x final and x initial. They both have their moments. And just watch out. I don't mean to do this, but sometimes you'll see me do v final x or just vx. And sometimes I'll say v initial x and sometimes v0x. All right. So there's that. If we go down to here, so this is at the bottom of page 22. There's a problem solving strategy. So I think I alluded to this briefly yesterday, but remember, the first step is read carefully. Then use that reading to inform these next 3 steps here. You really need to read, draw decent sized pictures. I like to say about a quarter of a page, meaning a quarter of the size vertically on the page. If you don't draw big pictures now, to be honest, you could probably get away with it. But later on in the semester, if you don't have big pictures, you're going to be in trouble. All right. So you just run out of room to label stuff and trying to squeeze it in, and then you make mistakes because it's poorly labeled. Just make your pictures big. All right. Then you've got a list of knowns and unknowns. You've got equations, list in equations. And then it's useful right before you start doing any math to just make sure you know what you're solving for. For example, earlier today, I literally misread the question the first time and I caught it right at this step. So it's useful to just make sure you know what you're solving for before you waste time on the algebra. Then you need to do problems algebraically. You just have to do it. It's the right way to do it. It's faster. It's got so many benefits. You might not be used to that. You might be used to always having numbers. We need to break you of that habit. And then finally, you could stick in numbers at the end of the problem and you could check. These are some things you could check. Do the units make sense? Does the answer seem reasonable, or is the plus or minus sign sensible? Are we on the right order of magnitude? Is it about the right size? If you know some information about real life, maybe that can help you think through that. Next, on page 23, I'm not going to do these problems, but some students are they're not used to this, or it's been a long time or something. If you need some problems with numbers, page 23 is for you. Now, I'm not going to do these, but I just want to point out there are some problems there that you could do. Now, I want to start on page 24 today. Okay. And again, the goal here is to deal with purely algebraic problems. All right. We want to do problems algebraically. Why? 1, it's just faster. 2, it's easier to check units at the end of the problem. If the units don't match, we can go through the algebra and look for a screwed up sign or a missed square root or something. And then if you do that, we can sometimes correct all this without having to punch in a bunch of numbers already. So it's just, again, that makes it faster. the third point is, if you give this result in terms of algebra, right, you could plug in different numbers and see how things change without having to start the problem from scratch every time for each new set of initial speed or acceleration values. And finally, you could use algebraic answers to create simulations or to check simulations, right? Eventually, we want to be able to code physics. And so we need to be able to have something to type into our computer code. And that is the algebraic formulas usually. All right. That said, let's start by looking at question 2.2. Okay. So what I'm going to do is I'm going to write down, like, let's say this was your test question. I'm going to write down everything I think you should write down on my whiteboard, but I'm going to do that without you looking at it. And then I'm going to show you my whiteboard. So you could write down what you think you should do, and I will write down what I think you should do, and we could compare. So go ahead. This will just take a minute. I'm going to go ahead and leave it on the screen while I do this. So I'm going to draw this. Problem 2.2. Okay. All right. So I took a second to do this. This is what I thought should happen with that. Whoops. Crawl over here. All right. So what I did is I drew the picture and I put some key assumptions right over in here, right? These were some things. We were supposed to assume that there's no friction. We're supposed to assume the box has negligible size. And then I can't read this from back there. The box is released from rest. G is some constant we know. We see that there's an angle here. We're told the length of the ramp is L. So I put that in the picture. It says this was released from rest, and there it is moving. I drew my coordinate system in red. That's a habit I kind of got into from chapter 5. So later on, I'll try to draw that in red just so it pops. That's all. I don't know. Any questions about this? You get it all on your paper, so you don't have to keep going back and forth to the book and looking for stuff that wastes your time. You get all your assumptions here. These are the key assumptions. Every engineer starts a problem by listing what is given, what is known, and what are the assumptions. All right. So maybe we could even explicitly write that. The things that are given to us. Now, this might seem weird to you at first, right? When you're first doing this, you're like, wait a minute, this is just a bunch of letters. I don't have any numbers other than G. look carefully at the problem statement. Let's bring it back up. And I'll point out a few things. It says the length of the ramp is L. When it does that, it says, assume L is a number I'm going to give you later. L is a known. Even though it looks like it's an unknown quantity, we don't have a number for it, but this is implying that that is going to be one of the things that I do tell you later. All right. And then in here, let's read the first question and see what that says. It says determine the angle required to reach the bottom ramp in time t. So time is a known. So I just want to point out this is a typo. That theta should not be there. That's actually what we're trying to solve for. Apologies there. Okay, so we're trying to figure out the angle required to reach the bottom of the ramp in this time t. And notice we're trying to answer in terms of these things. That means those are our givens. G, L, and T. So if you want, we could even state that explicitly. And what are we looking for? In part A, what are we trying to find?
Angle.
Theta.
So WTF is theta. What to find? I'm sure that's what you were thinking. What to find is theta. All right, old physics joke. Okay, next. Okay, we've drawn our pictures. Typically, what I like to do at this point, just so I have some room to work here, I'm going to make a little chart. I know this is a kinematics problem. We're in chapter 2. Later on, this might not be so obvious, but right now we know it's a kinematics problem. So I'm going to write down the kinematics variables in a list. Delta x, v initial x, v final x, a sub x, and time. I'm just going to make a little chart here. Okay, so in this case, let's go through these variables one at a time. We've got it all listed up here in words, but I'm just going to tabulate them so it's less thinking in my brain. And this is how I did it in the solutions, just so it makes it quick for you to check. If you're wondering, what did he use for delta x in this problem? There should be one of these charts on almost every problem in the solutions. And don't forget, if this is too slow for you, you could always get the solutions out and just start racing through as many homework problems as you can. And I'll give a shout out whenever I think there's something you should listen. So if this is too slow a pace, you can work faster and just get all of your homework done, okay? Let's start off. What is delta x in this problem? What does that mean? Go ahead.
L.
L, okay, sure. Should it be positive or negative, or is it always going to be positive for delta x?
Always
Positive. Positive.
It's not always positive, but it is positive in this case. I just want to point out, remember on, whoops, not this one. On the first 4 things in here, there's an I hat that we do not really write, right? Every single one of these things has an I hat. Does this go L in the I hat direction? Take a look. Yeah. Now, somebody out there might be thinking, and I'm sorry if I cut you off, apologies, but you might say, wait, this is going down and to the right. Shouldn't it be going negative j hat and positive I hat? Well, remember, I'm using this rotated coordinate system. Because this object moves in a straight line, why not line up that line with the x direction? Then we don't have to think about j hats. We don't have to think about up and down. We just say, this is the new x direction. So that's the same thing as just tilting the whole whiteboard, right? All right. So in this case, it goes from here to here. That's L in the positive direction. That's why this particular one is positive. Yeah, you could totally do that, Gonzalo. So, and that's a great trick. And you want to do this because it will save you time. Okay. So, good. Could you do it the other way? Absolutely. But then you have to think more, and we'll discuss that more in chapter 4, which is actually the next chapter we cover. So yeah, as we get into 2-dimensional motion, I'll explain more about when you might want to rotate and when you don't. Okay, what was the initial velocity here?
0.
Anybody? Zero. How do you know? What was the key word?
It was at rest.
At rest. Good. How about V final?
G sine.
Unknown.
Unknown. Okay, I'll just put a question mark for right now. How about AX?
G sine theta.
G sine theta. Should it be positive or negative in this problem?
Positive.
Positive. Why?
Same direction as the arrow.
Yeah. So again, we call down the ramp positive. So normally you think down is negative, but here down the ramp is going to be positive because we said so. And that's legal. All right. Einstein was somebody who said, hey, let's figure out this relativity stuff. I'm going to start with the first concept being coordinate systems should not affect my results. That was one of his fundamental tenets of special relativity. So we expect that should be true. The direction you draw this shouldn't affect the results. If you're worried, it won't. Okay, time. Oh, yeah, go ahead.
For the V initial X, that's 0 because it's at rest, right?
Exactly, at rest.
Okay.
And in case you're wondering, just to make sure, let me show you.
And the BF of X is unknown because we still haven't calculated it.
Exactly. Okay. Yeah. And just to be clear, just to show you the solutions. Wait, what problem is this one?
2.2.
Oh. Where is that one? This is the kind of stuff that I'm going to do in the solutions that you could see. So I'm going to try not just to tell you the answer, but at least for some of the problems, I'll try to say that in the answers. So again, if you don't like the pacing that I'm following, you could try to follow along with the solutions instead. And I've tried to put all this crap in there. So yeah, good question. In case you're wondering what, yeah. So, all right. Time, is this an unknown or is it a known in this problem?
It's known. It's
Yep. So I'm just going to call it T because it's some number that in theory we know. All right. And so this is what's weird. Basically, this looks like an unknown, but you're supposed to assume it's a known. Okay. This looks like an unknown, but we're supposed to assume it's a known. Why? The problem said answer in terms of those things. That means that's what we assume are known. All right. So is AX known or unknown? What do you think?
It's unknown.
Unknown. We know what G is, but we don't know what theta is. So technically there's a question mark right here. And remember, that's WTF. That's what we're looking for. Okay. Next step, write down some equations. Now, before you just blindly write them down, this is what I recommend. I recommend putting an equation here. And so for this, I happen to have it memorized. You might need to look it up on the back of your workbook or on page 21. But I know that delta X is V initial X times time plus 1/2 a sub X T squared. Rather than write the next equation immediately beneath that, I give at least 3-4 lines of space. That way I could do some algebra here if I need to, okay? Now the next equation might be like V final X. And at first, you might be thinking, I don't want to write down all these equations. I would recommend you do it. Just because on test day, you don't need to do it, but you will know the equations better if you do write them every time. And then pretty soon you'll have this memorized so you could write them so quickly, you won't have to worry about it anymore. And we use these in our codes all the time. So, all right. And then just to squeeze it in here so it is there. Sorry, I know I just told you to put space in there, but I'm not going to do it just for reasons that will come clear in a minute.
Would you be able to scoot it down, please?
Yeah. Sorry. Forgot to.
Thank you.
Yep. All right. So in this case, and definitely give out a shout every time I screw that up. All right. All right. Usually when I finish writing, I look on the screen to try and check for it if you don't want to. All right. Let's do this. Reread the problem. Remind me, what are we trying to do? Oh, yeah, that's right. Theta. That's actually why this is sometimes useful. If you have it written there, you stop reading. You just be like, oh, I know I need theta. Let's go through and see what stuff is known and unknown. In this first question, is delta X a known or unknown quantity in theory?
No.
Known.
No.
How about V initial?
No.
Known. T?
No.
No.
Unknown. This looks like a good equation. Agreed? We know everything except for A. Once we figure out A, we could get theta. So I wouldn't even bother with these other two, but you could do this like this. Well, what about this? I don't know that. I do know that. I don't know that. I do know that. This is not the best equation to start with.
So
However,
is A
go ahead.
is A not the downward force of gravity?
No.
Because it's not going straight down, right?
Okay, number one, A is acceleration. Acceleration and force are related, but not the same.
Okay.
And so so notice you're absolutely right. It's not G because the ramp is helping hold it up, which blocks some of the gravitational force, which causes you to have a lower acceleration than free fall. Is that okay?
Yes.
Yes, good, excellent. So, all right. Going down to this one, don't know, do know, don't know, do know. So we see that these last two equations are not where we want to start. I could point out very quickly, once you get this piece, you could figure out anything you want. So that said, I have very limited space. Normally you would not erase, but for me, I need to erase right here just so that I have some room, okay? So I'm going to get rid of these equations on your paper. You'd probably leave them there. Okay. The next step, maybe you're not listening. This would be a good time to listen. To save yourself a lot of headaches, before you do anything algebraically, plug in anything that is equal to 0 before you do the algebra, and it makes your life so much easier. For example, right here, this I could plug in. When I do that, look how much simpler this equation becomes. That's just a lot less scary to me. So plug in the zeros, now do algebra. Well, I could plug in these values if I want. X is L. A is 1/2. This is G sine theta. I get T squared. Wait a minute. Shouldn't the acceleration be negative? It's going downhill, right?
We rotated the coordinate system.
We rotated the coordinates, so down was positive. Oh, whew. Oh, I feel safer. All right. And so from here, I think you could solve for theta. Let's just pop it up on screen. And so there we go. What's something we should do before we're satisfied here? What should I do with that answer? Yeah, check the units. All right, now you might not be good at this, but we're going to do it every day so you do get good at it. What are the units of theta?
Unitless.
Unitless, and sometimes we also say radians. So we don't want to say degrees. So you could say either no units or radians. Traditionally, people say radians, but radians are equivalent to no units. All right? No units or radians. What are the units of a function? What are the
No
units?
units.
No units. Functions have no units. Okay, what are the units of the argument of that function? The stuff inside, what are the units of that?
Degrees or radians?
We would not say degrees. You could say radians. Okay. Actually, let me think here. I think it's just no units in this case, but basically no units or radians would be the same, but we definitely don't want to say degrees. Okay. The reason why is ultimately we may want to do calculus on this stuff. And if we did calculus on it, we want everything in radians. Okay. If you're doing calculus with angles, you got to do radians. That's just the way it is. Yeah, more on that some other time. All right, so now we have 2L over GT squared. We're told it should be no units. Let's see if it is. What are the units on top?
Meters.
Meters. The 2 has no units, so it just sits there. And then we got what? Meters per second squared times second squared. We're good to go, right? No units, as it should be. Check. All right. So that looks good. You could do some reality checks. Here are some examples of that. There's the unit check if you didn't see all that. All right, so that's pretty good. Now, any questions about that first part? That's the basic idea there. It's a little weird when you don't have numbers, so you have to know how to read the problem, identify which letters are givens, which are not, write your equations, solve for the unknown variable. All right, let's go back here. So at this point, you could plug in some numbers. That's fine. And there's some other information. I'll let you do the rest of these parts at home, but I just wanted to start that one. Before we get too far ahead of ourselves, I want to see how problem 2.3 is different. Again, I know you could do algebra, and if not, very soon you will get very fast at the algebra if you actually do your practice work. So I'm not worried about your algebra chops as much as I am you practicing setting up the problems. If you can't set up the problems correctly, you are toast. So let's see how you do on 2.3. I'm going to hide my whiteboard from you, draw what I think you should write. I want you to try and draw it. And remember, make that picture big so it's easier to label. Go ahead. I'll catch up. Okay, the block is kicked, it slides up the ramp. After the kick, it's moving up the ramp of length L with some unknown velocity V0. Its acceleration is still g sine theta down the ramp. So it's basically a similar block, similar ramp. So I'm going to assume it's still frictionless. Comes up when the angle is theta. All right. So in this case, the givens to me look like, let's see. Okay. So maybe there's more I could say, but this is what I got. Let me see if you got that too. I put the problem number, I drew my coordinate system, the block is going up V0, and it looks like WTF is V0 in this problem. So we have a different set of knowns. G, L, and theta are the knowns in this problem, okay? All right. Any questions on that so far? Okay. I'm going to write my list here. So I'm going to say this one, maybe I'll do it with X final and X initial, in case you're curious. So let's say there's X initial and X final instead of delta X. You could do it either way. Okay, let's go through it and see what we know. What do you think X initial is in this case?
0.
0. Why not start with, unless you have some significant reason to do otherwise, assume the initial position is 0. Some problems we might want it non-zero, but for this one, let's just start with 0. Okay. Let's see, what's X final in this case?
3/4 of L.
Exactly. It's not L. So you have to make sure you read the whole thing, and it says it only goes 3/4 of the way up the ramp. So that's why it's 3/4 L. All right. Sorry, that's a 3/4 there. Scoot a little closer there. All right. How about V initial X?
Unknown.
Unknown. And I think the problem called it V0. So you could say it's a question mark, or you could say WTF, just to remind yourself. V final X.
0.
0. How do you know that?
Because when it reaches the top, it's gonna like stop and then go back down.
Okay. Did it say that in the problem or something?
I don't know if it did. I just know it does.
It says it
I
comes
think it
to a
said it
rest at
stopped.
3/4.
So it comes at rest.
Yeah. Okay,
Oh,
cool.
yeah.
So it said something in there. Cool. At rest, whatever. So nice job. That's a 0 right there. And then AX, what's AX?
Negative G sine
Yeah.
theta.
How did you know it was negative in this case?
Because it's going against the what's it called?
Coordinate
The
system.
slope. Yeah. The coordinate
Outstanding. So we said up is positive. The acceleration is still down the ramp, but whoops, sorry. The acceleration is still up. We said X is up the ramp and it's accelerating down the ramp. So that's why. Okay. All right. And then the time in this case, I think we don't know that, right? There we go. All right. So looking good. What's the next thing you would do?
Write down equations.
Write some equations. And then let's take a look. I'm going to shortcut things a little bit. I'm going to write this equation.
Is the G sine of theta negative because it's going the opposite direction?
Of the coordinate system.
Okay.
It's not because it's going down. It's not because it's going to the left. It's because of these two facts combined. Coordinate is up.
But it's
The
opposing.
acceleration is opposite that. Yeah. So it's the combination of these two arrows. If they're going the same way, plus. If they're going opposite ways, minus. Good?
Yes, thank you.
Nice.
Quick question.
Yes.
All these equations are we supposed to memorize, or are
Well,
we gonna-
you got, they're on the back of your workbook in case you forget them.
Mhm.
But I tell you what, if you do a few problems like this, I think there's somewhere in here right there.
Yeah.
Now, so, and I usually give out equation sheets on tests anyways,
All right.
but if you do 10 of these problems and write the equations every time, like I'm asking, you'll have it memorized because we're going to use them over and over again in chapter 4 too. So it's probably worth your time to memorize them, but you just look at it and double check and you'll see, you'll have them memorized in no time.
All right.
Cool. But definitely not required. On test day, right? You can look at the back of your book. You can use your workbook and say, what did I do here? Problem is you don't have a lot of time. So you don't want to waste time like that. Okay. All right. Good comments. Others, other questions. Good stuff. All right. So what's the next thing I would recommend doing here?
See which ones are zeros.
Yeah, see which ones are zeros. We could also quickly check if this is known or unknown. I might do that really quick. So this is unknown, known, known, known. And that's why I grabbed this equation. So once you get good at it, you don't need to write all the equations. You could just say, wait, I'll look at the back and say, do I know this or not? Oh yeah, this is the one I grab. And then you don't write all three. All right, so I did that, let's say. Plug in the 0. So that's here, right? Let's see. Just going to get a little closer here so you can read. Lower this down a bit. All right. What was the acceleration? G? No, it was negative G sine theta. So now I don't have to keep looking at the picture.
Is delta x x final minus x in?
Absolutely. X final minus X initial. That's right.
Thank you.
Good call. Better to check, right? Okay. And so that's how I got
final the known.
V final in this problem was 0. V initial is the unknown.
Okay.
Is that right?
You put a question mark above the V final. That's why it confused me.
Oh, whoops. I missed. You're absolutely right. I screwed up. Right here. Is that better?
Yeah.
Yeah. Sorry about that. Thanks for catching that. Does everybody agree? Sorry, I was in a rush to talk about the next step and I forgot. I wasn't paying attention. My bad. All right. Now, check this out. I'm going to subtract this over to the other side. I'm going to simplify that, and I think you get minus like that. Now, before we go too far along, I want to talk about this. To be clear, minus V naught squared is equal to minus V naught squared. But minus V naught squared is not equal to minus V naught squared. Well, think about this. Think about right here. If you plugged in a number, no matter what, like let's say you plugged in -7. If you plugged in -7, then you squared it, you would get positive 49. When you bring it to the other side, it had better be a negative 49. So, or think about PEMDAS, right? You do the squareds first, then multiplication by -1. So that's why this is the same thing. You're first doing the squareds, then the negative sign. You do not want to do this. So I'm just stressing that. You probably knew that, but just trying to remind you if you're wondering, does this cancel this? No. This will cancel that. See that? This doesn't cancel the minus sign. That does. Okay. Enough said. So that means I could actually say this cancels that. And now I could solve for this. Like that. Watch out. In a physics class, especially with this equation, there's something you should always do when you take the square root. What is it?
Minus?
Plus or minus. Always be thinking about it. Sometimes the minus sign matters. In this case, what do you think?
It doesn't because it's going up the plane.
Exactly. It's initially going up. We should probably just keep the plus sign. So it didn't matter in this case, but this is a very common minus sign. Sometimes it's actually there. Nice job too, all of you. Good job in the chat as well. All right. So just kind of giving you an idea there. All right. Any questions about that process? What should we do with this answer before we feel good?
Check the units.
Check the units. What are the units of this 3 halves?
Nothing.
Nothing. G is meters per second squared times meters. What are the units of a sine function?
Nothing.
Nothing. Square root. You'll see sometimes I end my square roots like this. That's just helpful in really long problems. You know where the square root ends and the next part begins. In this case, let's see, what do I get? Meters per second. Does that
Keep
seem?
the board down again.
Yeah, sure. Just a sec. Thanks. Sorry about that. So far, so good. Meters per second squared for this times meters. When you square root it, you get meters per second. Looks good, right? All right. Other questions? I'm going to pull it back a little bit, try to show you the whole thing now. I don't know if that helps, but whatever, the units are good. All right. Anything else?
Quick question regarding homework. Where should
Yeah.
we be at currently?
So if you're like me, we're really, you feel like overwhelmed and really behind. Yeah, I feel that way too right now because there's just so much at the beginning of the semester to do. So if you could finish up chapter 1 and 3 pretty darn quick, that would be highly advisable. I think by next week, I want you into chapter 2 homework. Okay.
All right, sounds good.
Yeah. I mean, ideally, you would hopefully be done with chapters 1 and 3, maybe today or tomorrow or even Friday. And then you could start working on chapter 2. You know, this might be a good weekend to get caught up. So either this weekend or next weekend, you need to be deep into chapter 2. All right. So by next weekend, hopefully you're getting closer to done with chapter 2. All right. Enough on that. Good question. Yeah. And yeah, you're probably feeling overwhelmed. I am too. It's just a lot at the beginning. Don't forget, while you're feeling overwhelmed, later on, there's a couple of weeks where we have catch-up weeks. There's a couple of weeks where I throw out the labs and it's just practice tests, right? So there will be time somewhere down the road to catch up, but it's not for a few weeks. So you're probably going to feel really behind for about 5 weeks. And then all of a sudden you'll have some time to catch up. All right. It will happen. Just keep pushing as hard as you can and just know you aren't going to be able to catch up till then.
So
Other
then
questions? Yeah.
Safe
go.
to assume that every week we should complete a chapter.
That would be ideal. And then
Okay.
the first week you got stuck with 2 because those 2 chapters, chapter 1 is supposedly easy and chapter 3 is easy as well. So compared to the physics chapters, it's just math review basically. But yeah, later on, chapter 10 is so horrible. I actually budgeted like a week and a half for it. So the reason I'm rushing so fast now is so that I can give you extra time on the really hard chapters. So yeah. Good questions. Others? All right. All right. So let's see. Yeah, it's bad. You don't even know yet, Jacob. You'll see. Yeah, it'll get really juicy. Week 6 is, I think, the first week you can have a break. Yeah. All right. Let's keep going then. So this all seems well and good, but this is kind of the simplest types of problems that we have. So now let's start to add in some complexity one level at a time until we get to gnarly questions. And that's where you need to be with these types of word problems. Yeah. So let's go back to a screen share. And I think I'm going to go to question maybe 2.36. I'm not sure what page it's on.
41.
Thanks. Yeah. So I sent you a Canvas announcement today showing this video. Do I still have it up? Let me see if I happen to have it up.
I think you sent it via email.
Oh, did I? Okay, yeah. So I sent it somewhere. However you get your Canvas announcements. I sent a video of this problem, so we could watch it later if you want, but let's focus on doing the problems here. Oh, thank you, Jacob. Appreciate that. So You don't need to watch that video now, or if you want to, it's 10 seconds. You could just hit pause and stop listening to me and watch the video. But you have a snail in a car driving at speed V. He passes this cop without noticing her. At the instant the speeder passes the cop accelerates. Okay. And then we're trying to get the maximum distance. So let's say we're trying to do this question. I'm going to do my trick where I write down what I think you should do on the whiteboard, and then you write down what you should think you should do. And if you want to get a visual for the problem, go ahead and watch the video right now. You've got plenty of time to watch that 10-second video, okay? It's going to take me a minute to get going here. Okay. 2.36. .36a. And maybe I'll give you a minute just to kind of get your brain wrapped around it, and then I'll start talking to you. So I'll just let you take a second to think. Write down whatever you think. Maybe try without the solutions, if you can. All right. So maybe you're working ahead. That's great. Maybe you're not. Maybe you have no clue. Let's just take a look just in case. So here's one of the things that I'm thinking about here. All right. So we're looking for the maximum distance of separation. What I did is I did two different colors, one for the cop and one for the speeder. And the speeder goes flying past the cop. Man, look at that S car go. Jokes on Zoom. Horrible, but I do it anyways. All right. Next, if it's at constant speed, we know the acceleration is 1. Aha. The acceleration is 0. I put a subscript 1 on there because I'm going to have two different problems. I need to keep track of them. You could do subscript S for speeder and a subscript C for cop, or a lot of times it's going to be easier just to do number scripts. So I labeled the speeder as object number 1 and the cop as object number 2. That way I could say V2 initial equals 0, A1 equals 0. V2 initial was 0 because it starts from rest. All right. Questions about that? Okay. Why is this bad? Why is what I'm about to do bad? Why is that not good?
Because we don't actually know the distance.
True. Should these two catch up to each other?
We don't know.
Well, we know it's not well, think about this. Do you think the speeder will get ahead of the cop?
Yes.
So do you think the maximum separation is 0 or some number bigger than 0?
Bigger than 0.
So it's clearly not going to be there. That's when it's like catching up. It's somewhere, there's some distance between them. Otherwise, you don't have any separation, right? So, okay, that's cool. What do we know? These words are supposed to cue you into something. When you say maximum distance of separation, there's a physics thing you know. What is it? What do we know about this?
Acceleration has to be greater than 0.
Oh, that's true. What else? We already knew that.
Their velocities have to be equal.
Yes. And this is not obvious at first, but think about it. You start from rest. This one's getting ahead. This one's pretty slow, so it keeps gaining on it. And this is what you could see in the video if you watch later. It's hard for me to describe this, but if you watch the video, what will happen is when this one passes, you'll see a gap form. And then right about here, the gap will get as large as possible. That's max distance of separation. That occurs when they have the speed. How do I know that? Think. As soon as it's a second later, this is still accelerating. It's going faster. Well, if this is going 60 miles an hour and that's going 30, it's going to close the gap. So the idea is the gap is as large as possible between them when they have the same velocity. All right. And this is a new piece of information you're supposed to know. So if you've got your book, just give me a second. What I would do is you're supposed to know this. It doesn't tell you this. You're supposed to know V2 final equals V1 final. That's the trick. If that is the case, you get this. Since we're right here, let's mention this too. It says overtakes the speeder. When it says overtakes the speeder, what are we supposed to know?
The acceleration.
Nope.
That it's going faster than the speeder.
That's true.
Also, the velocity.
The positions are equal. Think about it. If he overtakes, if she overtakes him, we will know they have the same position at that instant, right? That's where they meet. So this is basically saying, when does the cop catch the speeder? Well, if they meet up, they're at the same position. If they're max separation, they have the same velocity. So you're supposed to know that and never forget for the rest of your life. Got it? What a treat, or at least for the next 3-4 semesters. All right, so put that in your workbook. Let's get back to the problem now. Any questions about that before I stop the screen share? Okay, sorry if I cut you off. All right, now it's exactly the same as every other problem. What I would do is just split the page down the middle. This side could be the speeder. This side could be the cop. If you could color code it, great. If you can't color code it, that's fine. But you've at least got the subscripts to go from, right? So in this case, whoops, let me do this side purple. All right, so in this case, we know delta x equals, now I got to put subscripts on them all. Delta x1 is, I don't know. V1 initial is V. How do I know V1 final is also V? Because it said constant speed. That means if you're at constant speed in a straight line, your acceleration is 0. If you're at constant speed, you could have acceleration if you're turning. More on that in another chapter. I don't know what the time is, so I'm just going to, but I do know this. I know that this one, let me just write this out really quick. I know that these two have the same exact time. So I don't know what it is, but I do know it's the same. So that allows me to drop the subscript for that one at least. Oops. All right. So over here, what do we know? Do we know delta x2? I don't think so. V2 initial is 0. It
Zero.
started from rest. V2 final, that was what we just spent so much time talking about. It's V, and A2 was just the value A. So now we can keep track. Oh, whoops, I should probably be careful over here. This should be an A1, right? It's 1's acceleration is 0. 2's acceleration is rate A. All right. Do I need to worry about minus signs on any of these?
No.
No. So we're at least we don't have to worry about that on this problem. Everything's going to the right. We got it. Okay. So far so good. At this point, what would you do next?
Start choosing kinematic equations.
Choose some equations and go to work. And so in this case, what are we going to try and figure out? What are we trying to find? What is WTF?
The distance.
The
Max
distances. Okay. So do you think we could get X1 or X2? Which one do you think we might start with?
Would you start with
It should
T?
be equal, right?
Are they equal?
Between, we're looking for the max separation, right?
That's right. We are looking for the max separation. So do you think X1 and X2 are equal?
No.
No.
Oh, no.
Right? So yeah. Okay, good, good. So this one, there's not much to do here. So I'm going to actually go over to this one and see. I'm going to get a little bit lazy and just say that delta X2 is equal to 1/2 A T squared. Now what I did is I plugged in the 0. Obviously, I'm just running out of room is the issue here on the whiteboard. So in this case, all I did was I grabbed the delta X equation, plugged in the 0, and then I plugged in A here, and that's it. I don't know if that helps. Do we know the time?
No.
Let's go to the next equation. V initial is 0. Wait a minute. V2 final is V, isn't it? Does that get the job done?
Yes.
Still don't know T.
We don't know T, but do we know both of these?
Yeah.
Yes.
So then we could get T, skid in there and get X2, and we've solved the problem, right?
No.
No. Shoot. What would we have to do? We could
we have to
use
find delta x1, right? And then,
Yeah.
and then subtract them.
Well, delta x1 is if A is equal to 0, distance equals rate times time, right? Plus a 1/2 AT squared term that goes to 0. Well, we know this is just delta x1 equals VT. So everything hinges on getting this time. So we solve for this time. We check the units before going on. Meters per second divided by meters per second squared. Well, that's the same thing as meters per second times second squared per meter. The units check. Seconds for time. I do that before I waste time plugging in. right? You check the units before you waste a whole lot of time. What if you accidentally flip this? I do that all the time. You probably will too. You just sometimes write things backwards. Checking the units can help you catch that mistake before you spend all day plugging it into the other equations. We check the units. Now I can bring this back up. I take this t, I plug it into there. I take this t, I plug it into there. Which one is the answer?
It'd be delta x2 minus delta x1.
D, the distance between is the larger one minus the smaller one. Which one is that?
X2 minus X1. No, X1.
X1. Now here's a trick. If you weren't sure, just slap an absolute value on it, right? I'm running out of room. I got to do this down here. Sorry. There we go. Now, if you wanted to, if you weren't sure, you could stick absolute values on there. So, yeah. But it's the bigger one minus the smaller one gives you the distance between. What do you think? Pop this up so you get a view of the whole problem here. Go ahead.
At this point, shouldn't it be x1 minus x2?
Oh, I said that, but yeah. Oh, you're right. But since I
Okay.
threw the absolute value on, you're right. You're absolutely right. I totally screwed up. I said it right and then wrote it wrong. I'm so dumb. Whatever. Yeah, this is supposed to be delta x1 minus delta x2. But since I threw the absolute value on there, technically I could say, oh, I was just blah, blah, blah. All right, cool. You're right. So now that I wrote this, I don't need the absolute value. It's the bigger one minus the smaller one. Sorry. Good job. I don't know. I think we all think 2 is a bigger number than 1. So we have this tendency to write 2 minus 1 all the time. But yeah, that's probably what's going on. Who knows? What do you think? Making some sense? Let me get out of the gallery view here. Any questions? Okay. Now, I think there's other parts of this problem. Maybe let's take a look at that. Hold on. Let's see what else is there. Okay, so that was all part A. Whoo! Next. How far from the origin is... Okay, so basically this one. Here's my question on part B. Part B, we're looking for when the cop overtakes the speeder. Can I use this same work or not? Is it going to be exactly the same or will it be different?
Would it just be flipped?
What do you mean flipped?
Like in this case, the cop would be the speeder, but the speeder would be the cop.
Nope, that's not going to do it. So we know the cop always starts from rest in this problem. That was a good thought, but that's not right.
Is this a 2-stage problem where you have to create a whole new?
Well, we've got stage 1 effectively and stage 2. So this is a 2-stage problem. There's a cop stage and a speeder problem. However, I don't recommend trying to use this and then split. I wouldn't, no.
When a distance are equal to 0?
Say again?
When delta x1 and 2 are equal to 0?
No, delta x1 and 2 equal to 0 would be right at the start. You're on the right track, though. It has something to do with the delta x's.
When they're equal to each other?
When they're equal. So instead of doing this, what we do is say, I need, and what else is true? There's one other difference. This is no longer true. Agreed? If the cop catches up to the speeder, the cop must be going faster. Let's look. Let me show you in the solutions just to show you how they look different. So one of the things you get in the habit of is you think part A sometimes relates to part B. They're similar, but not the same, and you can't just do it. So let's look at here. Look at that S car go. All right. Let me get this just a little. This is the picture for part A. This is the picture I recommend for part B. Do you see the difference? The cop is going to be going faster now. And as a result, we don't know what this is. We still don't know these things, but we could do this. We know they finish the same, so this is what's new. In the last one, we had to find the time using the velocity equation. In this one, we're going to find the time using the x equations. If I could scroll down just a hair. By setting the two x equations equal, let's just get all the way into it there. So I'll pause and see. Notice you get a different time. You get all kinds of different stuff. All right. But the moral of the story, that particular question isn't that exciting, but we do want to think like this. Part A and part B can have more than one difference. And it looked like the speeder didn't change at all, but the cop had two different changes, I think. Or it had one change, and then there was one equation that changed or something. So more than one thing can change when you change parts of a question. I don't know if that made any sense, but yeah. Any questions on that?
So for that, do you suggest that we rewrite all of the like kinematic variables, or should we try and reuse?
You know, I don't know. I would say this: we're all rushed for time, and our habit is to do as little work as possible, so that, but still get it correct, right? So that's really the advice. But what does that mean? For me, it's probably just start all over. You could see that's what I did, just because when I try to cut corners on these problems, it ends up taking me longer because I get confused more often, and then I want to strangle something, and it just drives you crazy because you're like, and then you end up starting over anyways. So for me, I would just start all over, but that's just me. And start each part from scratch, unless you know otherwise. The key is, Jake, I think that was your question, Jake, experience. If you have experience, you know when you can cut corners and get away with it. How do you get experience? You do the homework yourself, and then try to avoid using the solutions all the time. Okay. If you use the solutions all the time, I know exactly when to do things in the right order, and I did it all for you, and you think you know what you're doing. Then on test day, you're completely just incapable of doing even the simplest problems because you were just following along too much. So you really have to use the solutions a lot at first and then stop using them. And when we get to the practice tests later on, there's weeks for practice tests. Remember, don't use the solutions at all during your practice test time, and then grade your work. And if you do that a couple of times, you'll find out what you don't know. But Jake, you probably are, I don't know, you're pretty good with that, right?
Yeah, I'm decent with it. I just, like last semester, I would, like you said, I would get confused because I'd just sit there and reuse variables.
Yeah.
So I think
sometimes it's faster just to rewrite and start all over.
Yeah.
Confusion ends up slowing you down more than your writing speed. Yeah. Okay.
All right, cool. Thanks.
Good question. Yeah. Others? Yeah. Physics is just tough. It's tough because you have to practice more than you do for other classes. You just can't get away with being a lazy student. You might think you know what you're doing, and then your teacher changes one thing, like part A to part B. They look the same. The words are all the same except for one sentence, and then your whole process is completely different. So experience matters more in a physics class. You just have to do the practice. That's really the deal. If you do the practice, you're going to rock it. If you don't, you might get stung with a problem you haven't seen and just waste all day on it. All right, let's keep going. Now, we have a in-class activity at 6:15 is when it starts. So my goal is to take our break at about 6 o'clock, 6:05, make the breakout rooms before you leave, And then when you come back, I could just throw you right in the breakout rooms and we do the activity. So I'm going to keep pushing for about, what did I say? About 15, maybe 20 more minutes. Then we'll take our break. Okay. That said, let's try and do as many problems as we can. So let's just go down the page. All right. What would be different if this is how the problem is phrased? What would be different if we're doing 2.37? It's not so important to solve the problem as it is to set it up. And I believe this is one of your required problems. So we're working on those already. Let's just kind of write this one out. You do what you think. I'll do what I think you should write, and we'll discuss. Okay. They're going to start getting weird. .37. And if you've already started, I want to do 2.37b for reasons I'll explain in a minute. Let's do 2.37b. We spent a lot of time on the last problem on part A. This time we'll spend a lot of time on part B, okay? So 2.37b is what we're working on. Okay, so you've had a second to kind of digest it. I'm going to show you the most important thing on part B. The picture gets trickier. We're looking for the distance the cop travels to catch up, right? So I know that the cop and the speeder have to be at the same position at the end. The issue is the cop is not accelerating for the whole time. The cop is going to accelerate for a portion and then drive at top speed for a portion. This is a three-stage problem, right? There's stage one could be the speeder just driving around. Great. Stage two could be this one. And this one we could call stage three. There's three different stages for us to think about in this problem. Two for the cop, one for the speeder. Now what do? We write three kinematics problems. Now, I don't know if you could see this, but there's going to be a distance here, delta x2. There's going to be a different distance here, delta x3. And this distance up here is delta x1.
I did have a question.
Go ahead.
So I saw like a part where it said 25% greater than the top or than the speeder. So
Sure.
where would that be?
I'll show you that
another
in
stage?
just a second.
Okay.
That's one of the things I was going to address. Good job. That's a tricky spot for sure. Let me mention this first and then come back to you, okay? In the last problem, right? We said, well, the velocities were equal or the positions were equal. What is the relationship between these variables this time? What's the relationship?
Distance.
Okay, yeah. Give me an equation.
x2 plus x3 equals x1.
Yeah, that's what I was looking for. Do you agree that the two stages of the COP should add up to the displacement for the one stage of the speeder? Right? And what happens, we see, as these problems get nastier and nastier and nastier, it becomes more important to write these types of equations. These are the equations that link the different stages. I call that a constraint equation, right? We know that the total distance between these two is equal to that one. Got it. Now, somebody said, I don't know who was asking that question, but you were saying, what about the velocity here? Right here, it says 25% faster, right? That means that velocity is equal to, I'll say that's the velocity of the COP, the top speed, is 25% more than, that's 1.25 times V. Did that address your question, whoever asked that?
Yeah, I did.
And so, right, so 25% is 0.25. So 1V would be the same as 1.25 is 25% more than. If it was 25% less than, you'd say 0.75, but then the cop would never catch the speeder. All right. At this point, I'm going to go to the solutions. You should probably work this out on your own, but I think we got the most important thing. This one was an issue, and finding this constraint. Oh, there's another one more constraint. There's one more equation that relates these three stages. What is it? What else is related between these things?
Time.
Time. The total time is equal to. So we see we have two constraint equations plus this weirdo fact. All that is coming from the words of the problem. And so this is what's hard for people. You're supposed to read the problems, and some of the words have meaning that have that give special meanings to the problem. And then you also have to know how to do with ratios, percents, and what create your own mathematical relationships. This is a complex process that it's a lot harder than that first problem we did, right? So let's take a look at the solution and see if something jumps out at you that you have questions about. Obviously, you could do this on your own. But let's take a look here. This is the next problem, right? The graphs will ultimately help you. So let's look at part B here. I did the speeder. I called that stage one. The cop is accelerating. So there's that 25% more. Now, if you're wondering about fractions, who cares? We're engineers for the most part in this class. Usually you don't bother wasting your time with fractions here. For some reason, I just felt frisky. I don't know. But generally speaking, it's better to just do this as a decimal. But I did it with fractions for some reason. Oh, yeah. See, I went back to decimal in the end anyways. So why not just, yeah. Okay, whatever. Oh, and then see, please do not assume the fraction. Yeah, introducing the fraction was probably a dumb idea. It made me have to do more work. So I would just keep everything as a decimal, people. Don't waste your time with that fraction crap. But so here's our constraints. Here's our constraints. There's our list of knowns and unknowns. Think about those. Let's see. Does this make sense? The speeder, nothing has changed. Sorry, let me get my other marker here. The speeder, nothing has changed. That's exactly the same. This cop, they start at 0. They get up to this speed because the problem tells us with this acceleration. In stage 3, the cop stays at that speed with 0 acceleration. Why? Because we were told the cop travels at constant speed afterwards. I don't know any of the times. I don't know any of the delta x's. Look at this. How many unknowns do we have? We have 1, 2, 3, 4, 5, 6 unknowns. I have 2 equations right here. 1, 2. That means I need 4 more equations. So there's probably an x equation or a v equation here. This was the most complicated stage. So there's probably 2 equations there, and there's probably 1 here. So you could write the equations, solve for that, and you're off to the races, literally here. I'll let you work that out. Okay. Oh my gosh. All right. Okay. Now, I'll let you finish that up at home. Look at this though. Why is part A no different than the previous problem? What do you think? We're told part A is no different.
The max separation is always going to be when the person following is hitting the same speed as whoever they're following.
Exactly. So why do we not need that constant speed stage for the cop?
Well, they're going to hit V anyway, right? I mean,
they hit V and then they keep going and they're still accelerating. So they will hit that speed V before they stop accelerating. Agreed? Because the cop, we were told, stops accelerating at 1.25 V. So we know the max separation is completely the same. Tricky. All right, you're tired. We got 9 more minutes. Let's keep going. You're going to get a break. Don't worry. I want to show you something else. You might be saying, "Oh, this is all easy." Okay, fine. Great for you. Look at 2.38. Students usually have trouble with this kind of problem too. And so these problems, 36, 37, and 38, are really good because they kind of show you all the different ways you could have multiple stage problems. So I'm going to let you look at 2.38 for a second. So I'll give you till 6 o'clock and then we'll talk about it. Okay. 6 o'clock. So I'll give you another 2.5 minutes. You could try setting it up. Try not to look at the solutions for 2.5 minutes. I think you can do that. I'm going to explain it if you get stuck. So if you want to chat with somebody in the class or phone them or personal message them or whatever you want to do, I don't know, talk to whoever you want. It's a lot more fun in class when you can just talk to your neighbor. Hey, Dina, did you figure out my office hours at night on, or the 9 o'clock one is tomorrow night? Or I saw you tried to pop into my Zoom this morning. Was that just an accident?
Yeah, that was an accident. Yeah, sorry.
Oh, okay, that's cool. Switched. Oh, got the wrong Zoom link for class or something, probably, huh?
Yeah. Well,
Right. Okay, we can worry about it later. Gotcha. All right. I can't take it any longer. All right. What do you think? What kind of problem is this? 1 stage, 2 stage, 3 stage? What do you think? Anybody?
3 stage?
Okay. What are the 3 stages?
Cop accelerates, and then the time first he's waiting, and then he accelerates, and then he reaches the car.
Okay. And then the other one is the speeder, right? So this is 2.38. Oops. Okay, that's one. You could say there's the cop waits. So you said there's the speeder, which is number 1. Just drive it. Let me get that down. Okay. Then you're saying cop waits. You're calling that stage 2. And then the cop accelerates. I say you don't need to do that. It's actually, you can put this waiting stage into stage 2. So I view this as a 2-stage problem. And because otherwise it's impossible to, I think you'll see what I mean in a minute. And so that's what I wanted to point out is this one looks like a 3-stage problem. I agree with you. I think that was Alonzo, right?
Yeah.
Yeah. So that's a good idea. It's actually a 2-stage, even though it looks like a 3. And let me show you why. We're going to do an equation that looks like, all right, the speeder is still the same old boring speeder, x1, v1 initial equals v, v1 final equals v, a1 equals 0, time 1 equals I don't know, x1 equals I don't know. And then I don't know, is this when are they catching up to each other? Is that what they're doing? Oh, max distance between. Oh, okay. So my picture's bad here. Max distance between would be about right here, right? And they have the same V. So I misread the question. My bad. So now I go over here to X2. I don't know. V1 initial, or what? Sorry, V2 initial is still 0. V2 final is V because it's max distance between. So if we're doing max distance of separation, that's what tells us this. A is still A. Time 2 is still unknown. So it looks exactly like 2.36, but there's something different. It's a 2-stage problem. All this is correct. All this is correct. What's different than in problem 2.36? Or what else do we need? How do you get that delta T going?
So time 1 and time 2 are no longer equal.
That's what's different. In problem 2.36, I said, call this T, call that T. We solved this problem for T. We took that T and shoved it in here. That won't work anymore. This time and that time are not the same. What should we do? How do we get the delta T into an equation so we can solve for something?
T2.
Delta T.
Oh, go
ahead.
Yeah, go ahead.
T2 is equal to T1 minus delta T.
Let me think here. Let's see if this makes sense. You're probably right, but I have to think it through. Who is traveling for more time here? The speeder or the cop? Who's actually driving for more time?
Speeder 1.
Speeder, number 1. So does this make sense? The time of number 2 is time of number 1 minus a little bit. I think so. That looks sensible to me. It's T2 should be the smaller time, so it's T1 . Now, what if you say this the other way? Somebody else might be saying, well, Mr. Jorstad, I hate your class, and so I say it this way. I'd say, that's right, dadgummit, you have to pass. Ah! It's a long day, dude. I'm spacing out. Whatever. You could write it either one of these two ways. And some problems, this is advisable. Some problems, that it's just trial and error. At this point, though, the problem is now exactly the same as 2.36. We do the velocity equation. We solve for this time. We figure out what T1 is. We shove into here. We get the two distances. We do a subtraction. Ching, 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 ching. And now it's time for our break. Before you leave for your break, let me do a couple of things. Mark, let me see what Mark is asking here. Is that better? This is T2 equals T1 minus delta T. Down here, you could say that another way is T1 equals T2 plus delta T. Are you good, Mark? Sorry about that. Yeah, sweet. Okay, so let me do this. I'm going to stop the live stream. If you could do me a favor, don't leave.